Hello, students. This is Mr. Allen, and today we're going to start Chapter 7. Chapter 7 is all new material. In fact, from here on out, basically everything we do is going to be new content. So I need you guys to be really diligent about getting these videos watched before class. Today we're going to look at Section 7.2, which is integration by parts. We have two objectives. First is to find the antiderivative using integration by parts. And the second is use something called the tabular method. I do want to let you know that this tabular method really isn't required. This is something that you don't have to know. You do have to know integration by parts, but the tabular method is actually just kind of a more efficient way to use integration by parts if it's multi-step, which we'll talk about towards the end of the presentation. So what is integration by parts? Well, first of all, I'll tell you this. It's particularly useful when you're doing integrals that involve products of algebraic and transcendental functions. So I'm kind of telling you things that you don't know yet, but when we come back to this should hopefully make sense. So this is the most important slide in all of this presentation. This is the rule for integration by parts. The integral of u dv is equal to uv minus the integral of v du. Now here's some guidelines. I'm going to just kind of skip this slide, but I left it in the presentation. Again, this is something for you to look at maybe later after we've done a couple of examples. So let's look at example 1. Now we've already studied integration by the u sub method or substitution method for a long time. You're pretty proficient at it. You might think you can use u sub on this integral, but you cannot. But we can use integration by parts. Notice that this integrand is a product of a algebraic function and a transcendental function. So in order to apply integration by parts, we need to recognize that we've got something written in this form, the integral of u dv. Now there are several ways that we can think of this integral as being the integral of u dv. You could think of u as just being the x. You could think of the u as being the e to the x. You could think of u as just being 1. Or you could think of u as being x e to the x. So there's 4 options right there. Now everything else that's not u then has to be the dv. So which of these are we going to use? Now this is where integration by parts becomes kind of an interesting challenge. Well, it turns out that the guidelines on the previous slide suggest that we want to pick the u to be the simpler form of a function. So x is a simpler form of the function than e to the x. So that's what we're going to leave for our dv. Now I'm going to come back to this in another slide or two, but we're going to use this first option here to recognize this is the form, the integral of u dv. So if x, remember we said that x is equal to the u, right? Or u is equal to x. So then that means everything else has to be the dv. So now what does v have to be? Well, v is going to be the integral of dv. In other words, it's going to be the integral of e to the x dx. So if this is dv, so v is going to be the integral of that. And what is the integral of e to the x? Well, it's just e to the x. So that's nice. We already know that u is x. So what's du? In other words, what's the derivative of u? Well, it's going to be u. I'm sorry. Then if we do the derivative of both sides, you're going to get du. And then if you do the derivative of the other side, you get x. So now what we can do is we can plug all of these components into our formula. This is what we started with. Now here's what we're going to adjust it to. So the integral of x e to the x dx is going to be equal to, well, what did we say u was? U was x, so that's why we have x right here. What did we say that v was? Well, v was e to the x, so that's why we have e to the x right there. Now we need to integral v du. Well, v was e to the x and then du is dx. So we have converted our original integral into this product minus this new integral. Well, what is the integral of e to the x? Well, it's e to the x. So that's the answer. We have now integrated this expression before, we couldn't have done it with u sub. We couldn't have done it using any of the basic trig functions that we've already used. This is the integral. In fact, we could check that. If we did the derivative, Of course, if we do the derivative of c, that's going to go to 0. If we do the derivative of e to the x, that's going to give us e to the x still, right? And then if we do the derivative of x e to the x, we'd have to use the product rule. And when you do the product rule, you're going to get the following. You got to do 1, which is x, the derivative of 2, which is e to the x, plus 2, which is e to the x, times the derivative of 1, which is 1. So you get e to the x. And guess what happens to these e to the x's? They cancel out, which is exactly where we started with. So this is the solution. All right, so integration by parts. Here's a summary of some common integrals that you would want to use integration by parts. I'm not going to go through all of these. Again, I'm giving these to your reference. So there's an example here where it's, you know, if you have something like x to the n power e to the x, which is an example of what we just did. Here's an example when we have x to the n, but now we have a logarithm of x. Again, slightly different. And then here's one where you have e to the x and then like a trig function like sine or cosine. You'll get to experience all of these as you're working on your homework. All right, so before we go on to another example of an integration by parts, of course, the first one was the easy one, the easiest. I want to mention this Liate is what I call it, and it's just a mnemonic device, kind of like please excuse my dear Aunt Sally, and we use it to help us decide what to let u. If you're not sure, we just talked about in that previous problem where we let u equal x, what to let u. This is a mnemonic device to help you make that decision. Now, I want to forewarn you, this doesn't always work, but it works 95% of the time. It works most of the time. And remember, you can always check your answers with these integrals. So L stands for log or logarithm. So if you're looking at your product and there's a logarithm, let that be your u. If I is for inverse trig function. In fact, let me just go through the rest of these. A is for algebraic, T is for trigonometric, and then E is for exponential. So what I'm telling you is, like in the example that we just did, we had x and then e to the x dx. So what you want to do is you want to start going down this list and you want to say which one of these things comes first. Well, there's no log, so we're not going to do that. There's no inverse trig. But there's algebraic. That's algebraic. So that's what I let u be. Notice that exponential's down way at the bottom. So you usually don't let u be the exponential unless it's, you know, the first thing that you got that, you know, is in the list. So anyways, so Liate can be very helpful to help you pick your u. Let's look at another example here. So here's an example. This is similar to the first one, except now instead of x, I got x squared. Instead of e to the x, I've got the logarithm of x. Okay, so sorry, I'm kind of monitoring some students making up an assessment. So if we use the Liate, we probably want to use u equaling, oh, and I should mention this. Remember, our formula is the integral of u dv equals uv minus the integral of v du. Okay, so what are we going to let u equal here? Well, Liate says the first thing we want to look for, well, logarithm, it's right there. So we're going to let that be the ln of x. If that's u, then what's dv going to be? Well, dv has got to be all this other stuff. So it's got to be x squared dx. So now notice this integral is written in this form. U is ln of x, dv is everything else. Now, if u, and I'll leave this in purple, if u is ln of x, what's du? What's the derivative of ln of x? Well, the derivative is 1 over x dx. And if we know this is dv, then what would v be? Well, now we have to integrate, and the integral of this would be 1/3 x to the third, and that would be your integral. So now we have all of the components that we need to do our integration by parts as such. So this is going to be equal to, and let's do this now in Let's go back to red. So u, which is the ln of x, times v, which is 1/3 x to the third, minus the integral of v. Well, v again is, and I'm going to write this a little bit different. I'm going to write it this way. Oops. 1/3 x cubed, and then I got to do my du, and du was this. So then I got to multiply this by 1/x dx. So now I have converted, and by the way, now you see why I type most of these, is my handwriting is not very good. I have converted our integral into this new form, which gives me the following. I'm going to write this as x cubed, it's cubed, ln of x all over 3. Now I've got to integrate this. Now before I integrate, let me make a note here. Let's do it in green. You'll note that this x and one of these x's will reduce that to 2. So this is going to become minus 1/3, and I've got x squared there. Now I'm integrating x squared, so that's going to be x to the third divided by 3, and then plus c. And remember, this is multiply. So it looks like my final answer here, and I'll do this now in black, is going to be x to the third ln of x divided by 3 minus 1/9, and then x to the third plus c. That's the answer. Now, I highly encourage you, if you don't believe me, and you probably do, but if you don't trust yourself on one of these, just do the derivative of what we just got. Do the derivative of this and see if you don't come up with what we started with, which is x squared ln of x, and it will. Okay, last thing here. Let's talk about the tabular method. In problems involving, and I haven't done an example of this, so I'm going to kind of leave this to you guys. It turns out that sometimes when you do this integration by parts, you do it once, and then you find out you're left with an integral that also needs to be integrated by integration by parts again. So this can actually repeat. In example 7, I should not have said that. We're going to see another example. All right, so here are some common forms that you're going to need to use repeated integration by parts. When it's x to the n sine a of x dx, or x to the n cosine ax. Anyways, if you get one of those, you have to repeat the process. Let's look at an example of using the table method. Now I'm telling you, and I would encourage you, stop the video right now, try to use integration by parts here. And I'm just telling you, in order for you to do this integral with integration of parts, you have to do it more than once. You have to repeat the process. But I'm going to use the tabular method. Here's how it works. First of all, you are going to be alternating your signs, plus, negative, plus, negative. Now, what would u be in this case? Remember, we're going to use that whole Liate technique, right? So Liate, let's see here. Do we have any logs? Nope, don't see any logs, so I'm not going to use logs. Do I have any inverse trig functions? Nope. Do I have an algebraic one? Yes. So I'm going to let u equal x squared. So what I'm going to do in this column here in the middle is I'm going to do u and its derivative. So x squared, what's its first derivative? 2x. What's the derivative of 2x? 2. And then go to 0. Stop when you get to 0. Then the other piece is going to be v prime, or the derivative of v. So this right here is v prime. This is sine 4x. What is the derivative of sine 4x? Well, it's negative 1/4. I'm sorry. And it's antiderivatives. I'm getting confused. Sorry. We're doing the antiderivatives now. What is the antiderivative we're integrating? So what is the antiderivative of sine 4x? Well, it's negative cosine 4x, but then we have to do that 1/4 there because remember, we're doing the opposite of differentiation. And then we go again. So this goes from here. Remember, we're using antiderivatives here. Now we're going to go from here to here. Again, we're going to do the antiderivative. Now, so the antiderivative of cosine is sine 4x, but again, you've got to pull out a factor of 1/4. And then we got to do it one more time. So we have 4 rows of things, okay? So now we've got these arrows. So I'm telling you that the final answer is going to be as follows, and I'll show you on the next slide. It's going to be this times this minus this times this plus this times this. So the first term is going to be negative 1/4 x squared cosine x. Then minus and minus, so that'll be plus 1/8 x. So anyways, I'm going to show you the answer on the next slide. So here's all of those things that I was kind of explaining. Now let me just tell you that we use the tabular method when we have repeated integration by parts. You do not have to do the tabular method. You can just do repeated integration by parts and you will get the same answer. The tabular method, though, once you do enough of these, you'll see that there's a pattern, and that's what the pattern is, and that's the tabular method. I think I'm going to stop there. You guys need to practice these. I would encourage you to do the homework, but more importantly, you might need to do some of those extra problems that I included on the module. Have a good day.